Hello all, welcome to the basics.academy. This is Smart Contract Security, Fundamentals and Auditing, a 5 units, 3 credit course in the BSc Blockchain Technology program. Let's get into it. Today we are going to start with Unit 2, Secure Solidity Foundations. We are going to cover types and visibility, the difference between using msg.sender versus transaction.origin, and we will get into the depths of payable, fallback, and receipt. The main topics for today are data types and storage locations, value versus the reference types, and when it comes to storage locations, we are going to look into storage, memory, and call data. Coming to visibility specifiers, there are 4 visibility specifiers in Solidity: public, private, internal, and external. When we declare a state variable with public visibility, Solidity automatically defines a getter function for that variable with the same name. Then we are going to look into message.sender versus tx.origin and find out the reason why authorization logic must never trust tx.origin. And at last, we will look into payable, fallback, and receipt. How a contract accepts Ether it wasn't explicitly asked to accept. By the end of this lecture, you should be able to explain from memory why a contract that authorizes users with tx.origin can be drained by a single phishing transaction. Let us look into value types and reference types. What are value types? The example of value types include Boolean, unsigned integer 8 to unsigned integer 256, which can be used to represent only positive numbers, then integer 8 to integer 256, which can be used to represent both positive and negative numbers. Then we have address payable, bytes 1 to bytes 32, and enum. What is the behavior on assignment of value types? They are always copied. A new independent copy is created. Whenever you are assigning a value type, then it is always copied. Let us look into reference types. What are the examples of reference types? Arrays, structures, mapping, string, and dynamic bytes. What are their behavior on assignment? They are passed by reference within the same data location. Copying across location creates a new copy. For example, if my name is Batman and my friends call me Peter, then Batman and Peter both are referring to me. So this is a reference type. One thing to note or keep in mind is that reference types always declare a data location. Whenever you are referring reference types in the smart contracts, you are bound to specify the data location. The data location can be either of storage, memory, or call data. What is storage data location? It is permanent, on-chain state, and the most expensive place to read or write. What is memory data location? It is temporary and it is erased between external calls. It is cheap, mutable within a call. Let us say you have a function add. Inside that function, you are making use of a variable sum. Now this sum variable will be available only during the execution of the function. After the function executes successfully, the garbage collector will clear out the sum variable. And at last we have call data. So call data are read-only, non-persistent. These are the cheapest option for external function inputs. If you have external functions, then you can pass in the function arguments. If at all it is using reference types, you can give the data location to be called data because they are read-only and the cheapest. Let us now look into the visibility specifiers. What is a specifier? From where they can be called? And what are its typical use? Public specifier. This is callable from anywhere. You can call it from within the contract, from outside the contract, or from the derived contracts as well. What are its typical use? State variables, you want an auto-generated getter for general purpose functions. When you declare a state variable, having public specifier, Solidity automatically defines an getter function for that variable. External specifier. These are called via external messages. You cannot call external functions from within the smart contract. However, if at all you have to call external functions from within the smart contract, make use of this dot followed by the function name. Functions only meant to be entry points from outside the contract. Internal specifier. It is callable from within the same contract and from the derived contracts. Private specifier. Only this exact contract, not even derived contracts. Most of the time in interviews, a question is being asked, what is the difference between internal and private? So internal can be called from within the contract and from the derived contracts, whereas private can only be called from within the same contract. Private and internal restrict solidity level access only. So private and internal, these restrict solidity level access only. All contract state lives on a public blockchain. The important thing is anyone can read private storage directly from chain data. Never rely on visibility to hide secrets. The most important point is when you use private or internal, so these perform restrictions at solidity level only. All the contract state lives on a public blockchain. So anyone can read private storage directly. Hence, it is recommended to never rely on visibility to hide secrets. So let us summarize. We have 4 specifiers. Public can be called from anywhere, outside the contract, inside the contract. External can be called from outside the contract. If you want to call it from within the contract, use this dot, the function name. Internal can be called from within the contract and from the derived contracts. Private can only be called from within the same contract. What are automatic getter functions? Marking a state variable public, it does 2 things at once. First, allocates storage exactly like any other state variable. And secondly, it generates a getter function with the same name, returning the current value, no code required. For example, here we have a registry contract. Inside registry contract, we have declared a state variable balances, which is of type mapping. We have declared a state variable balances, which is of type mapping, having specifier as public. Now what the compiler does, the compiler generates function balances with an argument address account, external view, what it returns, unsigned integer 256. These things are generated automatically. So whenever you are using or declaring a state variable, having public visibility, in that case, the compiler will automatically generate a getter function for that state variable. For mappings and arrays, the generated getter takes the key or index as a parameter and returns a single element. It never returns the whole structure. So this is all about automatic getter functions. Let us now look into the global variables msg.sender, and tx.origin. What is msg.sender? The immediate caller of the current function. The address that made the most recent call in the chain. It changes with every external call and every internal call between contracts. Here, let us take a look at an example. A calls B and B calls C. Now, inside B, A becomes the message.sender. And inside C, B becomes the message.sender. Got it? What is message.sender? The immediate caller of the current function. Here, A calls B. So, inside B, A is the message.sender. And B calls C. So, inside C, B is the message.sender. I hope this is clear. Let us now take a look at tx.origin. The externally owned account, or EOK, that originally signed and broadcasted the transaction. Right? So, the example is A calls B. Inside B, tx.origin is A. And then B calls C. However, inside C also, the tx.origin is A, because it is the externally owned account that originally signed and broadcasted the transaction. It is fixed for the entire transaction, no matter how many contracts the call passes through. So, message.sender changes on each interaction or each message call, whereas tx.origin remains the same across the entire transaction chain. By tx.origin, authorization is a severe vulnerability. Here we have a wallet contract. Whichever wallet or account deploys this contract becomes the owner. Then we have a transfer function, and inside transfer function, we are checking that the tx.origin must be equal to owner. If that is the case, then go ahead and do the transfer. However, when you rely on tx.origin, there are chances that you can be scammed into performing this or calling this function. How can that be done? Let us look at the attack sequence. First, the owner is phished into calling a malicious contract. Let us say this is a malicious contract and I have phished the owner to call this function. Okay. Then, now remember, the owner has called this function, and the important characteristics of tx.origin is it remains the same across the entire transaction call. So, owner is phished into calling a malicious contract. The malicious contract then internally calls wallet.transfer. Now, when the malicious contract calls wallet.transfer, this check passes because this transaction was initiated from the owner wallet. So what happened at step 3? tx.origin is still the owner's EOA, the check passes and the funds move to the attacker in the owner's own transaction. So what is the vulnerability precisely stated? tx.origin always resolves to the account that started the entire transaction chain. An attacker only needs to get that account to sign one transaction into an attacker controlled contract. Once that is done, the victim never signs anything pointed at the vulnerable contract directly. The attacker's contract does the calling on their behalf, inheriting the owner's tx.origin for free. So it is advisable that you should never use tx.origin for authorization purposes. What is the fix? The fix is you are supposed to use message.sender. The same contract, a same transfer function, but the check is being done by using message.sender instead of tx.origin. Why this closes the gap? Message.sender is a direct caller. So what happens? The attacker's intermediary contract, not the owner. The check now correctly fakes, because even though the owner was phished into calling the attacker contract, and from within the attacker contract, the transfer function was called, since here we are using message.sender, So message.sender here is the attacker contract which is not equal to the owner, hence the check passes. Checks are performed on the immediate relationship, exactly what an authorization check should test. Did the account I trust call me directly? An OVAX rule of thumb, tx.origin has essentially no safe use in access control. Reserve it for pure analytics or logging, never for gating logic. So never use tx.origin for authentication purposes or authorization purposes. Always use message.sender. Let us now look at the payable modifier. By default, a solidity function rejects any ether sent with the call. However, when you use the payable modifier on that function, it removes that restriction. In simple terms, if you want to send ether to a function, that function must implement the payable modifier. And the ether that is sent to the function is accessed inside the smart contract in the global variable message.party. Apart from sending each to the contract via the payable modifier, even your address can be of type payable. When we say an address is of type payable, what happens? The address payable is the only address variant which has dot transfer and dot send functions available on it. And on functions, payable lets the function accept message.value. Without it, sending ether reverts the whole call. The fallback function. The fallback function executes when a call to the contract doesn't match any existing function signature, or when call data is present but no receive function exists. In simple terms, imagine your contract has three functions A, B, C, and you are calling your smart contract with function D. In that case, the fallback function will kick in. So here it is an example of fallback. External payable. It runs on unmatched function calls or on plain ether transfer if receive is upset. If you are trying to send ether to your smart contract and if the smart contract does not have a receive function, then also the fallback function will kick in, or when you call a smart contract with a non-existent function, then also the fallback function will kick in. It is triggered by an unrecognized function selector or call data plus no receive defined. It must be marked payether. Why? Because to accept ether. What are the common real world trigger? A typoed function name in a front-end call or a proxy contract intentionally forwarding every call. Suppose the functions add a double d and you have invoked only a.d. In that case, the fallback function will kick in. So two things to remember. The fallback function kicks in, right? The fallback function kicks in whenever there is an unrecognized function selector or a plain ether transfer in the absence of the receive function. Let us take a look at the receive function. The receive function is a dedicated entry point or plain ether transfers. If you have defined a contract and you want that contract to receive ether, then you must define a receive function having visibility external with the payable modifier. Now it runs only when message.data is empty. It is triggered by plain ether sends with empty call data, example dot send dot transfer or a bare call value x. It cannot take arguments or return values. It must be external payable and a contract may define at most one. There can only be one receive function. It cannot accept any arguments. If it doesn't exist, a plain ether sends false through to fallback instead, if that is payable. Otherwise, the transfer reverts. If your smart contract does not have a receive function, then the call will go to the fallback function provided the fallback function is payable. If not, the transfer will revert. If not, the transfer will revert. Let us try to understand when does a receive function run and when does a fallback function run. If the incoming call has empty message data, if the receive function is defined, then the receive function is executed. If the message.data is empty and no receive function is defined, in that case, the fallback function is executed provided the fallback function implements the payable modifier. If the fallback function doesn't implement the payable modifier, in that case, the transaction will be reverted. When the message.data is non-empty and there are no matching selector, that is, you are trying to invoke a function that doesn't exist in your smart contract, in that case, the fallback function will be executed. When the message.data matches a declared function, in that case, that function is executed directly. What is the rule of thumb? Receive is the narrow, cheap path for someone just sent me ether. Receive is the narrow, cheap path for someone just sent me ether, and fallback is the broad safety net for everything else. Unmatched calls, proxy forwarding, or ether sends when receive was never ether. I hope this makes sense and you have got a fair bit of understanding of receive and the fallback function. Here we have a minimal deposit wallet. It has one state variable balances, two events received and fallback. We have defined a receive function with external visibility and payable modifier. It is used for plain ETH transfers, no call data. If you want to send Ether to your deposit wallet, when you send Ether to your deposit wallet contract, the receive function will be executed. Anything else that doesn't match a function selector, in that case, the fallback function will be executed. So, for plain Ether transfers, the receive function will be executed, and anything else that doesn't match a function selector, the fallback function will be executed. Let us do a revision of what we have accomplished today. First, private state isn't a secret. If you are under the impression that you are using private visibility, that means your secret is private on the blockchain. That is a misconception. It is still fully readable from raw chain data. Never store secrets in contract storage. Using tx.origin for authorization. It lets a single phishing signature drain a wallet through an intermediary contract. This we have seen when we were comparing tx.origin with message.sender. For getting payable on a function that should accept ether or on an address that needs .transfer or .send. If a function needs to accept ether, then you must add a payable modifier. If you need an address to have .transfer .send, then that address must be of type payable. No receipt, unclear fallback. It makes it hard to reason about what happens on a plain incoming transfer. If you have not defined the receive function, then whenever you are trying to send plain ethers to your contract, so that will be rejected, provided if you don't have a fallback with payable modifier. Let us do a quick knowledge check. The first question is, a contract's transfer function checks require tx.origin is equal to owner. What is the primary risk? The answer is B. A phishing contract can call transfer on the owner's behalf and pass the check. Second, which data location is read-only and used for external function parameters? The answer is calldata. Question third, A contract has no receive function but has a payable fallback. What happens on a plain ether transfer with empty call data? Fallback executes and accepts the ether. Marking a state variable public automatically generates a getter function with the same name. So let us summarize what we have learned today. We have looked into types and visibility. In types, we went about value types and reference types. And in visibility, we have looked into public, external, internal, and private. Then, for authorization purposes, we have checked into msg.sender and tx.origin and what are the harms of using tx.origin. At last, we looked into payable, fallback, and receive. So in next lecture, we are going to talk about error handling, wherein they will cover require, assert, revert. Then we will switch to custom errors and look into how custom errors are gas efficient. And we will talk about gas optimization, including why hard-coded gas stipends break down. One task from your end is, or for the students are, before Friday's lab, you must install Remix in browser. No setup is needed. All you have to do is go to the Remix website or Remix IDE on the web and reread this DEX code walkthrough. This is important before our Friday's lab. So this marks the end of lecture 1 for unit 2, secure Solidity Foundations. That wraps up this session. If it helped, like and subscribe so you don't miss the next one. Questions? Drop them in the comments below. See you in the next lecture.